All right, Algebrites, today we're going to use inductive reasoning to make conjectures, and you say, what? Because first off, what the Gehenna is inductive reasoning, and second, what the Gehenna is a conjecture. So as we approach that, let's see what you responded. What are the descriptions and what's going on for each one of these? All right, so add one more row, add a row on bottom, that has one more dot. And let me fix that. One on bottom. Boop, boop, boop. Boop, boop. So if I were to sketch it out, it's still a pyramid. Holy monkey, that was ugly. Try that again. Boop, 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 boop. Something like that. All right, how about B? Let's see. Is this thing rotating counterclockwise? Is this direction?
That's
Ah, good. All right, so we are going counterclockwise in this way. So now the arrow is at the 3 o'clock position, and then counterclockwise, so the arrow's at the 12 o'clock position. So where's the arrow going to be next? At what position? At the 9 o'clock position. So specifically, how much is it rotating? 90 degrees clockwise. So rotate figure 90 degrees anti-clockwise for you Brits out there. Whoo! Come back. All right, good. So each time we just add 3 every time. So 14, 17, 20. So add 3 to previous term. Or add 3 to get to next, to previous term. By the way, each one of these guys is called a term. This is the first term, that's the second term, the third term, the fourth term, fifth term. When you have a sequence like this. All right, and the next one here, a little bit more complicated. So how does it work? So with this one here, we add 1, so that's a 5, a 6, and a 7. Effectively, I'm just counting. And the same thing I'm counting on the bottom, just at a different, I'm starting at 2 instead of starting at 1. So each one of these goes on. Now notice though, at some point in time, there could be some, well, I guess not in this case. Disregard that. Talk about it in this case. What's the description? The term number is the dimensions of the square. Of square. So in other words, the 15th shape is a 15 by 15. So this all brings us to the wonderful world of something called inductive reasoning. Inductive reasoning. You already use inductive reasoning every time you make a stereotype, every time you say you always and you never, or hey, I love, this bird always comes every winter. Oh, that you've noticed a pattern. So this is the first thing. Observe a pattern. Observe a pattern. So step 1 is watching, paying attention. Number 2 is that you say something about the pattern. So we say make a conjecture. So there's a big word for you, and we'll define it momentarily, officially. So we make a conjecture. We make a statement about the pattern. And finally, what we do is we verify. We check our guess. We verify the conjecture. Now, there are 2 ways for it to go from here. Now, this is the reasoning process. Now, officially, though, if you verify it and it's a yes, then you now have a law. You now have a law or a theorem, like the law of gravity, etc. If you end up with a no, oh, it doesn't work. My guess, my explanation doesn't quite fit. Then you have to go back and make another conjecture. Another thing to call this besides inductive reasoning is simply the scientific method. scientific method. And you might use a word called hypothesis. So you state the hypothesis, then you check the hypothesis. So when you get into more lab sciences, you're going to explore this more. But this kind of reasoning we use all the time. With that in mind, let's define two things. Let's define what a conjecture is. So a conjecture is a statement explaining a pattern. Now, let me make sure, at this point in time, a conjecture is neither true nor false. At this stage, it's neither true nor false. At this stage, it's just a statement. We haven't said it's 100% or it's false or right. The next thing is a counterexample, and a counterexample is a statement or an example that disproves a statement. That disproves a statement. So, for example, you never call me. You pull out a call log. There you go. I called you in July. I just disproved your statement. That disproves a statement or a conjecture. Take a gander. We're going to verify the following conjectures. If it's false, we're going to provide one counterexample. All right, the product of an even number and an even number is even. And so we say to ourselves, well, maybe that's good. I just need to try that. So I'm just going to throw down some even numbers. I'm going to productify them. Hashtag. So 2 times 4. And in the end, I get ochito loquito. Okay. Let's try another one. 12 times 10. And what do I get? 120. Okay. So far, even times even is even. And we keep going. 8 times 6, 48. Hoi. So are there any other types of evens that I'm missing? Well, we could get into larger digit numbers. But at this point in time, we could probably say that yes, it's true. Now, there is a proof to it that requires letters, but we're not going to go into it. So at this point in time, I can't find, or I haven't found, a counterexample. But let's look at this one. The sum of two negative numbers is negative. On this next one, apologize for the misspelling. It's not month-a. If a month starts with the letter J, then it is a summer month. And you start thinking, oh, we've got July, we've got June. Now, these are examples that prove the statement. Anything else? Am I missing something? Call it out. January, great. So, in this case, January is not summer. So here is my counterexample. I do not say, oh, false. Some months aren't in the summer that start in J. I'm not interested in some. I'm interested in the exact one example who starts with J that's not in the summer. And L here, I apologize, so finish it up. You can connect any 3 points to form a triangle. And I'll just draw the triangle. So think. Sometimes you'll say, oh, well, here's one, and here's one. Clearly that's a triangle, so that's an example. Let's see, let me see. Oh, that's kind of an obtuse one. But then you get to this and you notice, oh, if I make it a straight line, oh, these here are not a triangle. In fact, we would call it collinear. So here would be my answer. So I would say that the conjecture is false, and here is the counterexample. But so now I could go back if I were doing inductive reasoning and change this. You can connect any 3 points to form a triangle. So how would you change this to be a true statement? All right, so in this one, we're going to use a pattern to set in each of these, and we're going to set up a table in order to make a conjecture, to see about how things relate to one another. So let's see here. When we just look at this, it says, what is the relationship between the segments drawn So when I say segments drawn, this is a segment, these are segments, these are segments here, and the sections formed. So here's a section, etc. So what we're trying to figure out is if there is a direct relationship between the red segments and the blue sections in my diagram here. So let's see. Segments versus sections. I'm just going to make a table. And remember, we could be wrong. So I'm going to leave room just in case we need to make an adjustment to my conjecture. So let's see here. Segments. I have one segment in the very first one that I can see, and I have two sections. Well, how about in the next one? 1, 2, 3 segments. It jumps to 3. And now I have 3 sections. Oh, jolly. Then I have 2 segments and 4. Oh, jolly. So sometimes if we look at the problem in a different way, instead of looking at just the segment as a complete segment, let's look at a specific segment, the radii. Radius, plural, is radii with a double I like that. So let's count the radii that we have and the number of sections that we have. So this is just an alternate way of looking at it. So notice here, on the very first one, I have 2 radii, one going north and one going south. So in this case, I have 2 radii and 2 sections. Now clearly the second one is easy. We have 3 radii, 1, 2, and 3. And then we have 3 sections. And then over here, what looks like a plus sign is actually 1, 2, 3, and 4 radii. And I get 4 sections. Now, what would you conjecture to be the situation here? Well, the number of radii creates the number of sections. The number of radii create or form that many sections.